Hello! Welcome back to College Physics. In the next few lectures, I'd like to start talking about Chapter 2 on kinematics. And Chapter 2 is on 1D kinematics. But we're going to learn, studying Chapter 2, 1D kinematics, the technique that could certainly be used to describe 3D kinematics. Because we're going to find out that 1D kinematics can be extended readily to 2 and 3D. You just keep repeating the same procedure that you did in 1D for each of the dimensions till you get up to 3D. So this is going to be pretty useful for us to learn. It's really basic stuff. And what's 1D kinematics about? Well, in 1D kinematics, we're going to define basic quantities, which are displacement, velocity, and acceleration, and learn how we can use these basic quantities to describe the motion of objects. So now we want to start off talking about 1D kinematics. We're going to start at the end in the textbook, Chapter 2. For this particular chapter, we're going to start 2.8, graphing. And say, okay, they're going to talk about graphing the position versus time of an object. So here we can see we're going to be graphing the x position versus time is what they're doing here. We're going to be developing these equations that describe what you see on the graph. We're also going to be graphing some other stuff here. We could be graphing position versus time, graphing velocity versus time, graphing acceleration versus time. So we're going to have to define all these things. They all have quite basic definitions that just rest on each other, just like building blocks. So let's go through each one and figure out why and how we're going to graph. And then we'll come back and learn, well, why is it important for us to understand how to graph a straight line, and so forth. So let's get into unpacking that. So we want to start talking about basic 1D kinematic. And that's just describing the motion of an object in 1D. So here we can see our object here is, I like to call him Mr. McDougal. And he lives between this chicken shack, a tree, and there's a couple of bricks that keep him corralled in here to this area. And they got an x-axis set up. And the origin, where the zero of the x-axis is arbitrarily defined to be right here in the middle. I think that's special features. You can reverse the x-axis, so you could make it so that the negative is to the right and the positive is to the left. But I just want to do it the regular way. Have the positive direction to the right, the negative direction to the left. But anyhow, the orientation of the x-axis and where the zero is, it's an arbitrary construct that we can add after the fact. You could just imagine, you could just take away this ruler altogether, and Mr. McDougal can live quite happily here and move around. So here, see, I have him, he's going all over the place. I'm jiggling him around. And all that motion of him jiggling around and moving and doing his thing, that exists completely independently of any description. So what's the point of kinematics? Well, kinematics gives us the tools to describe this motion so that we could then record it or reproduce it or send the information across the world so someone else could reproduce the motion. So it gives us the language to describe the meaning of the motion. Just like the English language is giving me the tools I need to talk about this stuff to you. The language, the sounds I'm making are completely independent. The sounds themselves don't necessarily have a meaning. We attach the meaning to them. It's the same with the kinetic description of the motion. The equations and the way we record it are just the way we describe what really happened, which what really happened is this guy's just moving around here in space here or on the ground. Okay, so that's the real thing. And the kinematic description is the language we use to describe it. So let's see how we're going to get into that then. So we'll go over here to charts. So we'll start moving them around. When we do, we'll see that there's three quantities that get recorded: the position, velocity, and the acceleration. So I can move him around. He goes hither and thither. And pause. And then we can do playback and play back what I just did. And well, you can see exactly what's happening. And so position is pretty clear. So let's just first focus on position. So here we plotted the position. Plotting the position, that's like plotting the x, his x position along the vertical direction, and time along the horizontal direction or horizontal axis. So what's that mean? And in the Moving Man Phet Sim, what were we plotting? We were plotting his position along the vertical axis. So in the Phet Sim, we plotted the position x in meters, so I'll label x in meters right there. That's what we plotted along the vertical axis. And then along the horizontal axis, we're plotting the time. So the simulation just has a clock, and at any given time, it just makes a dot where his position is. So let's say if we start off at 0, then the first dot is at 0. And let's say it makes dots every second, or every half a second, I don't know. It makes dots every defined interval of time, some short defined interval of time. So the next interval of time, it puts a dot, there's a dot, that's his position there. Then sometime later he's there, then here, then maybe here, here, there, and so on. Okay, and these are his positions at all the different times. Then what do? Well, then you just come along afterwards and just connect these all with a curve, like that. Just interpolate between those dots. And that's pretty much what this computer is doing, or pretty much how anything. We'll go ahead and plot position versus time. And we go, okay, well this gives us the x position, started off from 0, versus time. Very straightforward. So here's the plot of the position versus time then for our trip with Mr. McDougall. We can see here at time 0, he started off at a position of 0. Here later at 1.2 seconds, his position, as we can see, just a little past 4. And you come over here and go, okay, well, he's a little past 4. Here, this thing is marking. I zoomed in a little bit. You can see he's at 4.2 right then. Looks like about 4.2. So you can see exactly what's happening. Okay, so that's position versus time. Pretty straightforward, clear to understand what this is. Okay, what's the velocity? What are they plotting here? So now we'll look at the velocity. So the velocity versus time, as you can imagine, well, the velocity tells you how fast he's going and also what direction he's going. And in 1D, when the velocity has a plus value, then he's moving to the right, and when velocity has a negative value, he's moving to the left. Like you can see over here, okay, when the velocity is negative, you can see right for a second there, while the velocity is negative, he's moving to the left. Just like when the position is positive, then he's to the right of the 0 of the x-axis, and when the position is negative, it just means he's to the left. Okay, and you can say, okay, well, let's see, all along here, while he's moving from the right to the left, we can see the velocity is negative. And notice the velocity is jumping around all over the place. So what actually is the velocity that this is measuring? The graph is actually measuring what they call the instantaneous velocity. That is, it's the velocity right now at any given time, as opposed to the average velocity. We may have already talked about average velocity. If not, first off, let's define average velocity. And then once we define average velocity, we'll use that to define the instantaneous velocity. Let's see that once you get one, then you can understand the other. So we'll first define the average velocity, then we'll define the instantaneous velocity. Now we want to define average velocity and instantaneous velocity. To do that, we have to define displacement. We've already defined displacement, but let's look at the displacement over here, given this graph. So the displacement, just change in x. That's the displacement. Change in x, which is some final minus some initial x. For example, we could look at the displacement where the initial x position is when we start the clock at time 0. Here, see, according to this graph, and just for this particular graph, doesn't always have to be this way, when we started the clock, x was equal to 0. Right down here, here's the origin of the axis. This is where x and t are both equal to 0, right there at the origin. So we could consider delta x is going to be x final minus x initial, some final minus some initial value. And x initial doesn't have to be when t is equal to 0. It could be some other time. Let's say I make this x initial. Then at that time this would be t initial. And let's make this position x final. Then this is right down here would be t final. So what I'm saying is that at time t equals t initial, x is equal to x initial, and then a little bit later at time t is equal to t final, x is equal to x final. And here I'm calling whatever this is. I mean, this is going to be t in seconds. Maybe this is at time. Maybe this is a time equal to say 1.2 seconds, and then this time say is equal to 2.2 seconds, for example. And maybe here x is equal to 1.1, and over here say x is equal to 2.4 meters. So in this particular case, what would the delta x be? And I could also call it this. So sometimes I call it x final minus x initial. I also like to call this x minus x0. this means exactly the same thing. All I've done is then just said that instead of calling this x final, I'll call it x, and instead of calling this x initial, I'll call it x0. Sometimes one notation could be preferable to another. Generally, I like to use the simplest notation I can, just to save myself the trouble of having to writing too many letters. So that's why I prefer this one. It feels like it's just easier to write. So the change is the arbitrary change between any initial and final position that we like. Now the average velocity, v, and we put the over bar on it, we mean average velocity. That's defined to be the displacement over how long it takes to make that displacement. So in this particular case, the average velocity between these 2 points right here, this initial and final point, is going to be the change in, which is the final minus initial, over the time it took to make that change. And here you can see, okay, so the time it took to make that change is just the difference between 2.2 and 1.2, or in this case, so it's also the final minus initial. Delta t is the final minus initial. And you can see where that comes from. Final minus initial, that gives you the interval between these two. There's the time interval, that's the time interval, and here is the x interval. So this is delta t, that's the time interval, and here's the x interval, delta x, that we're considering. So for this particular case, the average velocity between these, the average velocity in this interval, the average velocity between this initial and final time is going to be equal to final minus initial. Doing the math, we just get 1.3 meters per second. So let's think for a second about what this average velocity thing we just cooked up here is. Notice how it's defined. It's defined to be delta x over delta t. The average velocity is delta x over delta t. And in this particular case, we chose the interval delta x is between finals 2.4 and started at 1.1. We could have chose any other interval for this and considered the average velocity between any other interval. For example, we could have chose the initial location x to be when x is equal to 0. So we could take x initial equal to 0, or x naught x0 equals 0, and considered some other final position, like say over here. Here it looks like x would have been about 1.1 again, but at a much later time, say maybe t equals 4 seconds or something like that over here. So we could have chose any interval. For this example, we chose this particular interval. But let's consider what this means. On this graph, notice what this is. Delta x is the rise, and delta t is the run. Rise over run. So this here, notice that the average velocity that we're talking about is equal to the rise over the run, where the rise is delta x and the run is delta t. Average velocity, rise over run. So do you remember rise over run? That should bring back memories from algebra. Remember, the rise over the run was the slope of a straight line. So and what is the slope of the straight line that it is in this particular case? Back in algebra, the vertical axis was the y-axis, and the horizontal axis was the x-axis. Now on the vertical axis we're plotting x, so x is playing the role of y, and on the horizontal axis t, so t is playing the role of x in that sense, but everything else is basically the same. So what line is that rise over run corresponding to? Well, it's corresponding to the line that would run between these 2 points. So in fact, if I were to make a straight line that ran between these 2 points, so here I've made a straight line that runs between those 2 points, and that straight line, that could actually represent another position versus time curve. Another position versus time curve that has what? The same rise over the run, has the same rise over the run, and it's also a straight line. This was a curve in space. X wasn't proceeding linearly in time. It was taking this curved path in time. Over here, here's a straight line that passes through these 2 arbitrary points, our arbitrary initial and final point, which we use to define the displacement delta x. And what is similar about that? It has the same slope. Any rise over any run, any delta x over delta t, for this guy right here, will have the same slope. In other words, if the object was following this path, this linear path, straight line path in the x versus t space, then what it would be doing, it would be moving at a constant velocity equal to delta x over delta t. So the slope of this line is that constant average velocity. And another thing, what could you say about this? If you're following this path, kind of an orange colored path, it's kind of dark orange colored path, and not the original path, the black curvy path. If you're following the dark orange path, what's going to be similar about your trip? Well, at time ti at 1.2 seconds, you'll be at the same x position. And then at time t final, here in this case equal to 2.2 seconds, you'll be also at the same final position. So at those exact 2 points, you will have the same time and position coordinates. And so that means if you're tracking the motion of this object starting at this time reaches the very same point that this object does. So the object following the black curve and the object following the orange curve go from the initial to final points. They start and arrive at the initial final points at the exact same time. So that means that the average velocity is the velocity that will achieve or give you the same result, that is, get you from the same starting point to the same final point in the same time as the variable velocity did. In other words, what I'm saying is the velocity wasn't constant along the original curve. The velocity changed in time, whereas on the straight line curve, the velocity is constant in time. But that constant in time velocity gives you the same result, at least between this interval. And that is the case with average velocity. That really is what average velocity means. Now let's look at how we're going to define instantaneous velocity. To do that, let's go back and look at the original McDougall path that we were checking out in the beginning. So let's look back at our original sim here, where we're following Mr. McDougall, and use our graphical kinetic description of his motion to see if we can understand how the simulation is determining the instantaneous velocity. That's the red curve down here below the position. So the position versus time graph, okay, so we understand that. That's just the same as like an x versus time. We'll just call the position x. And here's the instantaneous velocity. And they actually show the position and velocity for any given time here. They've got it recorded for us. So let's see if we can understand how they're getting the instantaneous velocity. So now we want to understand instantaneous velocity. And we understand average velocity. For example, I could find the average velocity, say, between this point here and this point here. So say between when we start the clock at time 0 and when Mr. McDougall reaches the furthest point of his journey to the right on the x-axis, we could find the average velocity. That is, the velocity that would get us between this point and this point in the same time as he did go with his variable velocity, because remember his velocity is jittery here. The instantaneous velocity is kind of jittering up and down, although the trend is overall to the right like this. Okay, what would the average velocity be between those 2 points? Well, if this was the, let's say if that was the x final, or the x, I like to call x final just x, and this was the x0, here in this case x0 would be equal to 0, then we just follow the same procedure. Here, just so the average velocity then would just be v average, would just be delta x over delta t. In that case, it would just be x minus x0 over t minus t0. Here, and in this case, that would just be x over t, because both the initial position and the initial time are 0 when we start out here, because x0 and t0 are both equal to 0. t0 equals 0. t is equal to 0 when you start the clock. So that's what it would be in that case, and we could figure it out, try to figure out numbers for these things, put those numbers in and get a value. But let's not worry about that. Let's look to see if we can figure out, okay, what is the instantaneous velocity at any particular given time. So let's say, what's the instantaneous velocity, say right in the middle here. So let's see if I could just guess my way to the middle, somewhere right there, so that there's the middle. Okay, what is the instantaneous velocity right at that spot? So how do we get instantaneous velocity? Well, it turns out And if you think about it for a second, this may make sense to you. The way the instantaneous velocity is defined to be the velocity right now at that point, but the instantaneous velocity, which we'll just call v instead of v bar for v average, is just equal to delta x over delta t, but in the limit as delta t goes to 0. That is, the instantaneous velocity is defined to be the rise over the run in a vanishingly small interval. That is, a vanishingly small interval of time. So basically, to do it in practice, what you do is just zoom in here on this spot. Let's see if we can figure out how to zoom in on this spot right here. So I gotta figure out a way to mark the spot. Okay, that's the spot we want to zoom in on. So I'll begin zooming in here. It's right up there. Want to zoom in on that spot. Just zooming in our camera close. And here, this seems to be as close as I can go with these toggle controls. Okay, now we've zoomed in on the spot. So our procedure for finding the instantaneous velocity at this spot is to take the velocity at a vanishingly small interval. Find the rise over the run for a vanishingly small interval close to this spot. So what I'll do is I'll go from here, then I guess we'll go from here, and then let's make the straight line between these 2 points. Then we'll back out a little bit. So here we're zoomed in, a little less, I zoomed out just a bit. Now notice this is the vanishingly small delta t, and here's our small delta x going up here. It should be vanishingly small. Remember, it should be in the limit as delta t goes to 0. The interval in the limit as delta t goes to 0. As a practical matter, we can't really let delta t go to 0, but we can let it become very, very small, which is what we're doing here, and then consider the line that passes between those points. And this delta, the slope of this line, as you can see, is the delta x over delta t. So the instantaneous velocity right at this point, I don't know if you can see it there, but it's actually this line that we've drawn, which has the rise over the run, that's equal to the instantaneous velocity at this point. So the instantaneous velocity at that point right there is equal to that delta x over delta t. And this is the slope of the line that's actually tangent to the curve, the blue curve, the curve of Mr. McDougall's actual trajectory. This line for the instantaneous velocity is the line that's tangent to the curve right at that point. That is, it's the line that just kisses the curve right at that point. Not quite so easy to see right here, but if we zoom in on it, we can see a little better that it's the tangent line right through that point. It's a line that just kisses the curve or approximates the curve itself right at that point. In fact, you could see this thing is blocking out the blue curve, right? So if we just were to replace the blue curve with a little snip of this line between the initial and final points right here, or the initial point, and here's the final point. If we just replace the blue curve with that little bit of line there, that little bit of line approximates the blue curve in that interval very accurately. And that really is the point of the tangent line. It's the line that just kisses the curve at that point. And the slope of that line, the rise over the run of that line, is the instantaneous velocity. That's the meaning of the instantaneous velocity. So if we were to look at instantaneous velocity at other points, like for example, what would the instantaneous velocity, say, at this point be? It would be the straight line that runs right through this curve. And we can see in that case, there's the rise over the run in that case. So if we're looking at the instantaneous velocity right here, v, this would be another delta x over delta t. That's a different delta x over delta t than that one. Give us an instantaneous velocity there. And we can see that instantaneous velocity is still delta x over delta t. But you can see that instantaneous velocity is negative because the slope is negative. And here you can see that the delta x actually, if you start here and go here, the delta x is actually going down. So the delta x is negative. And here then you have a negative velocity. So this velocity would be less than 0. In this case, the velocity is greater than 0. Because here you have a positive slope, velocity is greater than 0. Negative slope, velocity is less than 0. So now let's bring both curves together from the PhET sim and compare them and take another closer look at instantaneous velocity. Now we understand that the instantaneous velocity is just the average velocity but measured over a vanishingly small interval of time. and it's defined in the same way. It's the rise over the run of the curve. So let's see if we can use our knowledge to make sense of this FETSIM. So here's our position versus time curve in blue for Mr. McDougall, and down here in red is our velocity versus time curve. And like we said, what FETSIM is plotting is the instantaneous velocity. It's the velocity right now. That is, it's the rise over the run right up close as you get right in on the interval there. So let's see if it makes sense to us here. Here the velocity is increasing. Let's see, it increases up to a value of 6.238 right here. So if we zoom in right there on that curve, that means that right at that tippy top, that's the steepest part of the curve right there. And then the velocity jumps back down to negative. Does that make sense? Okay, if you look over here in this interval, just a little bit later, so think of the slope of a tangent line. The slope of a tangent line is the line that would have the slope at any given point of this curve. Right, so here the slope is going up, and then as you round this bend here, now it looks like, here you see the velocity goes negative down here. Here the velocity is negative, and where are we on the curve now? We're on a negative part of this curve. Right, the slope bent around, so the slope right here of the curve is going to be negative. The velocity at this particular spot here, at time equal 0.3 seconds, right around that interval of time, if you take the rise over the run, that rise over the run is minus 2.587 meters per second. That's the instantaneous velocity at that point, time 1.5 seconds. Okay, well we can see the position here is 5.224. The instantaneous velocity right there at that spot is 0.203 meters per second. And it's small right there, but actually you can see he's turning around. It would make sense that the instantaneous velocity is small right there because he's slowing up to turn around here. If you look at his motion here, let's watch. Let's play back slow. He comes up over here, he slows down, he turns around and then goes the other way. So here's going the other way, his velocity is negative. Just right over here at the spot at 1.5 seconds, his instantaneous velocity is 0.203. What would his average velocity be going from 0 to time 1.5 seconds? So if we want to calculate the average velocity between 0 and 1.5 seconds, what do? So the average velocity, V average, is always delta x over delta t over the interval. So here we want to go from here to here, from there to there. So what's it going to be? So the x initial, the x final in that case, we can see the final position, so let's just call it x minus x0 over t minus t0. So the final position we can see is 5.224 meters. And the change in time, t, the final time is 1.5 seconds, and the initial time, well, we start the clock at 0 in this case, so the initial time is 0. So it's 1.5 minus 0 is just 1.5. So V average is going to be 5.224 divided by 1.5. That's equal to 3.48 meters per second. And what does this average velocity do for us? Well, this average velocity is the constant velocity that would get us from point x equals 0 to point x equals 5.224 in the same interval of time. What's the line through these 2 points? The line through those 2 points looks like that. If we followed this curve, this curve, the slope of that curve has the average velocity. And if we follow along that curve instead of Mr. McDougall's original curve, then we would start at the same point Mr. McDougall started off and get to the same point at 1.5 seconds that he got to, that is when x equals 5.224 meters. We'd go between those same 2 points in the same amount of time with a constant velocity, and we'd get the same result, that is we'd make the same displacement that Mr. McDougall made traveling with his non-constant velocity. We can see his velocity was quite jittery. His instantaneous velocity was jittery over that time. But this was his average velocity between 0 and 1.5 seconds. Even though in the actual motion his velocity was jittery, right? Here was positive, then it even went negative here, then positive again. The overall trend was positive. And then here, of course, he's going back the other way. He turns around and he's already going the other way. So this is his instantaneous velocity. And his instantaneous velocity, what is that? It's the line tangent to his position versus time curve at any point. So the instantaneous velocity is the tangent line at any given point. We can see over here, okay, here's where the velocity is going negative. You can see over here, basically past this vertical slider right here, the motion tracking slider, we can see the velocity has gone negative over here and the slope of the line tangent is negative. Then let's see, right here, if we look at this point where he turns around, notice right there, his velocity is 0 at that point, right? So think of the line tangent at this point. The line tangent at that point is 0 because he's turning around. And notice, okay, so line tangent at that point 0, his velocity right at that point is 0, right, where he's turning around. So does that make sense? Yeah. And here, notice his velocity is 0 right at this point. His velocity is also 0 at this point. Anytime he's turning around, his velocity is 0. If you think about that, that has to make sense. Anytime he's turning around, his velocity is 0. Let's go to his playback, see he turns around. Let's start again. Set him to slow-mo, and we'll watch him go through. So when he gets to the top, he turns around just for a second, he stops moving and his velocity is 0. So anytime he turns around and goes the other way, just for a second, his velocity is 0. So anytime the tangent line to the blue curve is flat or horizontal, straight across, you have a 0 of the velocity. So right here, there's a 0 of the velocity here. Right here, 0 of the velocity here. Here, 0 of the velocity here. Here, 0 of the velocity here, and so on. All these places he turns around, the velocity passes through 0. He's wiggling back and forth, his instantaneous velocity. Oh, and here's something else that's interesting. Notice, when he starts his trip, he's at 0, and when he ends his trip, he's also at 0. So if we took, let's say, between 0 and 6 seconds, where he makes a round trip, if we look at the average velocity for his round trip, what would that be? It would be final position minus initial position divided by 6 seconds. What's the final position? 0. Initial position, 0. 0 minus 0 is 0. His total displacement is 0. Therefore, his average velocity is 0. Does that make sense? His instantaneous velocity flopped all around like we can see right there. His average velocity is 0. Does that make sense? It does make sense because remember, the average velocity is the constant velocity that will give you the same net displacement that the instantaneous velocity did over the same time interval. And since he made a round trip, his net displacement was 0, so you need a 0 average velocity to make that same net displacement over the time interval. All right, let's leave that right there. And when we come back, we'll look at the graphs a little more and see if we can use those graphs to help us cook up the kinematic equation.